let's go. 92, 93. Yeah. Check the two papers, get the LDA math behind LDA and see if we can turn it into ranking. So let's go look at the paper because we wanna find if we can make changes to this paper. Clinic-based MNL, topic evolution. No, pages and 215 to NEL 9. And we can go and speechify, trying to find anyone. Evaluating topic models for information retrieval in international conference on information and knowledge management. Oh, I see. What is it? I see. I am. And then another one in 2009, a comparative study of utilizing topic models for what is the difference? For information retrieval, a comparative utilizing the this one a European one, and I wanna check it again on internet.com and close the window before I come. Control and I wanna see if this model is very different one I see 93, 92. No. What are you looking at? Is it the screen or is it just me? This is better now. We are sharing something. A comparative study of human errors and evaluating topic models for information. We explore the utility of different types of topic models. Probabilistic and not for retrieval. We show that topic models are effective for document smoothing. Elaborate topic models that capture topic dependencies provide no additional gains. Smoothing documents by using their similar document is as effective as smoothing using topic models. Topics discovered on the whole corpus are too coarse-grained to be useful for query expansion. Experiments to measure topic models' ability to predict health and likely confirm past results on a small corpora, but suggest that simple approach to topic models are better. Download PDF, I wanna read it, and there is how many pages in this? It is only 2 pages. Are you making fun of me, my brother, man? It's pretty good. I was wondering. Zingy or Jingy, I don't know. This is only 1 page, it seems that's what it is. It is so amazing that we can find papers in 2 pages and I wanna read them very well. This is much longer. Topic models in information retrieval and needing. Sounds like a thesis parameter. Abstract list of table, list of figures. Alright, let's go read the 2 page and it will give the juice of what we wanna. No. Zingy and wine, PDF I'll lean in your suit, and the thesis on paper, and I wanna evaluating topic models. Just copy and paste their names at the tanks, and then we wanna find the seasons. There's la 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 la. This is another big paper, so I am worried about the results. La 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 la. Topic tracking model and closest is current tab and now. La 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 la. Learning evolution. Motherfucker, where did I put it then? Hold. No. Antithesis. Making hypothesis. Where is it? Most probably and not vertical problem. We showed that dummy models are effective for documenting. Moving to more elaborate dummy models that are no additional gains. There's similar that moves effective when we're using dummy models or determine on the whole. Two course grain to be used for query expansion and measure dummy models or vertical data information. Is also a small purpose suggest this. We know already that okay, this is bullshit. This is just bullshit. I already know it. Number of topics and relative log FEL log EL. Smooth MU, you can see LDA has the number of topics increases, but PAM has a NIPS data set. Relevance modeling. We also construct a special kind of topic model based on relevance then, which treats each document as representative of its own topic. What does that mean? Can you read it for me? I cannot read. I don't like to read. I even know it. I know it. And Speechify is where I wanna upload it. Just leave me log in, and where is the login? Welcome back and try it for free and sign in and sign in and sign in and sign in and add file from my laptop. The evolution of topic modeling. No, evaluating for information retrieval.
Evaluating topic models for information retrieval. Seenye and James Allen. Center for Intelligent Information Retrieval, Department of Computer. We explore the utility of different types of topic models, both probabilistic and not, for retrieval purposes. We show that, 1. Topic models are effective for document smoothing. 2. More elaborate topic models that capture topic
What? Why did you stop?
Dependencies provide no additional gains. 3. Smoothing documents by using their similar documents is as effective as smoothing them by using topic models. 4. Topics discovered on the whole corpus are too coarse-grained to be useful for query expansion.
Why do you stop?
Expansion. Experiments to measure topic models' ability to predict held-out likelihood confirm past results on small corpora, but suggest that simple approaches to topic model are better for large corpora. Categories and subject descriptors, H.3.3 Information storage and retrieval, information search and retrieval. General terms, algorithms, experimentation. Keywords, topic model, retrieval, evaluation. 1. Introduction. Topic models are a very popular approach for representing the content of documents. A document is assumed to draw its vocabulary from one or more topics. Topics are represented as probability distributions over the vocabulary, where differing topics give different words high probabilities. We infer a set of topics which can be used to describe the contents of a collection. The high probability topics and words within them can be viewed as a loose description of the collection, with better topic models providing better descriptions. A natural question is whether these topics are useful to help retrieve documents on the same topic as a query. Intuitively relevant documents have topic distributions that are likely to have generated the set of words associated with the query 1, 2. In fact, early research on topic models suggested that they might be used for information retrieval, IR, too, but it was not until recently that they were successfully applied to large-scale and realistic collections 6. Our goal in this study is to explore the utility of different topic models for retrieval purposes. Different topic models specify different document generative procedures, which can lead to very different topics. We use a selection of representative machine learning topic models, the mixture of unigrams, mu1, latent Dirichlet allocation, LDA, 1-6, and pachinko allocation model. Copyright is held by the author/owner. We also construct a special kind of topic model based on relevance modeling, RM3, which treats each document as the representative of its own topic. We first follow a standard machine learning evaluation approach to compare the document modeling performance of different topic models. 1. We calculate the log empirical likelihoods, log Ls, of generating a held-out test data from different models. 4. Then further divide the log Ls by that from the unigram model to obtain relative log Ls, RLTM, for better comparison. Thus, RLUnigram is always 1.0 even using different size test data, and low scores indicate better representation of the corpus. We first use a small NIPS abstract dataset with 1,647 abstracts from NIPS proceedings. Following 4, we split the dataset into two subsets with 75% and 25% of the data respectively. We train the models with the larger set and calculate likelihood for the smaller set. We use 50 supertopics for PAM, with the number of subtopics varying from 10 to 180. Figure 1 shows how the relative log Ls change with.
So this is just 2 pages. And this is 13 page, alright.
With different number of topics and different models. Our results are consistent with previous results for PAM and LDA always perform better than simple models, mu and RM, PAM performs the best. By viewing each document as a topic, RM performs better than mu, and close to LDA. We then use large-scale corpora for comparison, which has not been done before to the best of our knowledge. We utilize 5 large TREC corpora used in previous research 5, 6. They are AP, FT, SJMN, LA, WSJ, with between 90 and 242K documents and roughly 100 queries per corpus. For each of the 5 corpora, we split it into halves, training different models with one half and calculating likelihood for LDA. The other half. PAM has not been used in this comparison because its training is too expensive. Figure 2 shows the results on AP test data. It was surprising that the results on large corpora do not mimic those on small corpora. LDA has higher RL than smoothed mu. We speculate that smoothed mu performs better than LDA when using relatively small number of topics for modeling distributions of large corpora. 3. Document retrieval. There are 2 obvious approaches to including topic models in IR. The first is the document modeling approach, where we calculate PWD by smoothing the document with topics from different topic models, when smoothing the document with the highest ranked topic it is in and using the topic from MU, LDA, PAM, and RM, we have retrieval methods, CBDM5, BTLBDM, BTPBDM and RMDE1, respectively, when smoothing the document with a weighted combination of all topics that it contains and using the topics from MU, LDA, PAM, and RM, we have MBDM, LBDM6, PBDM and RMDE, respectively.
I don't see any effect
The
of
second is the
ranking.
query expansion approach, where we topics similarly add words to the query and run the revised query, when only using the most similar topic from MU, LDA, PAM, and RM, we have retrieval methods, BTCBQE, BTLBQE, BTPBQE, and RM1, respectively. When using all the topics from MU, LDA, PAM, and RM, we have CBQE, LBQE, PBQE and RM, respectively. 5 TREC corpora and queries are used again for evaluating different topic model-based retrieval methods. The same data had been used for evaluating CBDM and LBDM 5, 6. We use the full AP corpus for training and the other 4 corpora, FT, SJMN, LA, WSJ, for testing. The number of LDA, RM topics for MU and LDA is tuned to be 2,800 respectively. For PAM, we use 800 subtopics and 100 supertopics. We also include a simple language modeling retrieval baseline, QL, which does not.
Alright, let's check if the other paper has anything. Comparative.
A comparative study of utilizing topic models for information retrieval. Seenyi and James Allen. Center for Intelligent Information Retrieval, Department of Computer Science. University of Massachusetts, Amherst, Massachusetts 01003-4610 USA. Abstract. We explore the utility of different types of topic models for retrieval purposes. Based on prior work, we describe several ways that topic models can be integrated into the retrieval process. We evaluate the effectiveness of different types of topic models within those retrieval approaches. We show that, 1. Topic models are effective for document smoothing. 2. More rigorous topic models such as latent Dirichlet allocation provide gains over cluster-based models. 3. More elaborate topic models that capture topic dependencies provide no additional gains. 4. Smoothing documents by using their similar documents is as effective as smoothing them by using topic models. 5. Doing query expansion should utilize topics discovered in the top feedback documents instead of coarse-grained topics from the whole corpus. 6. Generally, incorporating topics in the feedback documents for building relevance models can benefit the performance more for queries that have more relevant documents. Keywords, topic model, retrieval, evaluation. 1. Introduction. Topic.
Alright, they're talking about something. Experiments 5 to corpora and corresponding. Alright, let's go over rank. For retrieval by using cross entropy as the ranking measurement. Lambda is tuned for each method. For the method using topics from the whole corpus for query expansion, like any we tune the number of top ranked topics for calculating relevance. For the methods using topics from the top K feedback documents. Tune the number K, we also tune the number of topics using the topic model. Set line. expansion. Let's go ChatGPT. User structure queries. Okay, it is the same problem we have. So they look at the top K document retrieved by the original query and expand the query using topic model based use topic. Okay, so it is related to what we are doing. Query expansion. So it is, right? So it is about ranking, but the effect of ranking is not model. But they are using LDA on topic model. Query expansion is about broad queries. But they are not doing it based on user behavior. They are using it based on the top K. So maybe it is already flooded, you know? So it can be relevant and it can be topic models on feedback. Let's read their conclusion. In this paper we can predict the technical topic model document models query expansion. What is a feedback? User click is a feedback document. I want to know description of the data set. See what papers cited this paper. Of topic models. Alright, these can be studied further, but So I want to read the abstract, sorry. So this was not the abstract. More elaborate loop gain. I mean, there's no math here, but yeah, this is too much math. So this is not thanks God. Are not discussed. No, they do not. Okay, so they're not covering this. You wanna go behind math of LDA, I think. We did this. So we say our documents are generated. Okay, the difference is quite simple. Difference between LDA and our model is quite simple. What does LDA says? LDA says words are generated based on topics. What are words or documents? Sorry. What about the length of documents? But each word in the document, how does LDA define? How does LDA model suggest length of a document? Our model says we have this cascade model that exit probability. LDA doesn't say so. Excellent question. I'm very sharp. You're asking, does LDA say anything about how long a document should be? Does it short and it does not generate document lengths explicitly, but it implies them through the generative process? How? LDA generative process. So we have first we have data, we have these topics, and we generate word. We generate a document D, sample topic G proportion theta D, which comes from the Dirichlet, that theta. For each word position n1 to nd, sample topic zn multinomial word repeatedness document. Where does nd come from? If LDA does not model nd, assumes your condition on a fixed length, which is not true in our case. So this is our main difference, if you want. Prior over ND, like Poisson distribution over length. Prior, we are using okay, and so we generate this first word and then other words the same way. So LDA. In standard LDA, each word in a document is generated independently given the document's topic mixture of given theta d and the topic word distribution. So theta d is fixed. Document D with ND. We draw the document's topic mixture, theta d, once we learn them for each word. Alright, so once we've set the theta d, the others are generated with that. Topic Cn. What's with it? Tractable and scalable. These are the benefits. Simplifies language task. All right. And now we are saying we have this cascade model. Cascade, how important is it? Honestly, I don't think it's that important. We could see that LDA still recovered those categories pretty good. It was not bad. should we do now? So they're not studying the effect of ranking. Topic modeling is just run independently generates awards and not based on ranking. We want to dive deep into their model. So tell me about the algorithm of LDA. Maybe we can add the cascade model too. Variables, topic word distribution, document topic mixture, and we also have the mixtures. Alright. Different documents. Assignment. Pair word topic assignment. What is Z? Documents, just a bag of words. We want to know fucking ranking. Data topic word distribution, data the document topic mixture. We can see the words. We can check it. So choose alpha data topics. Collapse keep sampling. We have the collapse keep sampling. Integrate out data into sampling. Belong to topic K. What is document D word N? DN means document D word N, and ZDN is its topic. This where N DK topic K document D minus DN number of words in document D assigned to topic K, number of times word W is assigned to topic K, number of words assigned to topic K, Dirichlet priors, vocabulary size. So this has a formula. Running over and over until the topic is stabilized. Once stabilized, take the D normalize. Similar effective doesn't require great interpretation. A large group run variational inference in original LDA paper. So okay, original doesn't give some simplified factors approximation posterior. Okay. Simple factorized approximation to the posterior. Theta z, q, theta, gamma. What the fuck is gamma? Phi was motherfucker. Use beta and then optimize theta phi, which is r, and gamma version. So take beta based on atomic word count. So we want to add the order of words. Theta mixture. Z is the topic assignment. What is it? Topics. Fast scalable determinism. Theta decanted topic and B, the K, K. Which topic was chosen to generate? So there is no effect of ranking in LDA. So that's important because the thing with our data set is that we always keep the order of the words the same. Like it's always 1 before 2, but in LDA it can be 2 before 1. Well, what if we sort them? What if we rank them, sort them? Words can be even repeated there. How can we add to LDA? Ranking to LDA? I think there is nothing we can add. Oh, we can. So we want to say the probability of this word being generated decays. Yeah. Especially in our case that we know our document has some structure. So we are giving our document more structure so we can have more freedom on the Now that we know have a decay factor, right? So our betas, which are our distributions, are, for example, a decay element. What should I say the decays? Betas are a distribution 1 to n, right? I want to say my betas are, for example, beta decay times, okay, ranking times beta ranking times beta of relevance. We can even assume beta of ranking, decay of ranking, because we are doing it in our own model queue. And our model is also simpler in the sense that our users are fixed. They are saying, no, for each document they are fixed also. WDN. What is WDN? Word in document D at position N, and N is less than or equal than D. Ah, beautiful. Observe word at position N in there. ZDN, what is it? The word in document D at position N is generated from a topic. It's generated based on a mixture of topics, right? Based on the theta D we have. I don't get the topic assignment here. Because it is supposed to be generated based on theta. Theta D topic mixture for document D, K simplex, right? For example, it is uniform, and with probability 1/3, we are generating from topic 2. Okay, why then ZDN matters? If it is 1/3, 1/3, 1/3, why does this topic 2 matters? I don't get it. Alright, it seems it matters. And beta K, word distribution for topic K. Okay, these are topics. -1. Alpha is for K elements. This is a parameter of the Dirichlet. Okay, Dirichlet prior for theta. Eta is RV plus. It's the Dirichlet prior for beta. Alpha for theta, which is the mixture, theta for beta. Which beta? We have K betas, but we are on the generative model. For each K, topic K, sample beta K is non-Dirichlet of eta. The beginning is it is the beginning, initialization. For each document D, then we are just, what we are doing is updating alpha and probably eta. For each document, instead of updating beta and theta all together, which is the biggest space, maybe theta and alpha are not that different still, but we are limiting ourselves to Dirichlet, which for sure makes the beta space much smaller. For example, theta D from Dirichlet of alpha, and for each word N between, okay, NDs are given. I think we don't generate them, but they're all less than a max ND. So for each ND, what we do is, for each document, you have ZND, determine that by theta D, and then use beta ZND, right? Beta of ZND. Sample beta of ZDN. Sample topic is ZDN based on theta, and the sample word WDN, multinomial of beta ZDN. Alright. Alright, I know what it's saying. So this way we generate our documents. This is the assumption how documents are generated. Like the way we had for our cascade model, that users are going through a cascade to generate it. This is how they assume it. They assume that there is no connection between words. Length is at most n. I want to change it. This is the cascade part. and joint distribution. The full joint likelihood of all variables. Why do you have probability of theta? I don't get this part, to be honest. Because theta is a distribution. Why do you say probability of theta? Z. Well, Z you can say. Z is a random variable. And alpha and beta. Given alpha, why beta? Why not gamma? The full joint likelihood of all variables, probability of theta d given alpha, then z given theta, and then w given beta of z. Exactly. Alright. So we first fix theta. That's the probability. Theta is given the alpha. Why should it be multiplication of them? I don't get this one. Alright. Because theta d is itself I know that, but I feel this notation is wrong. ZDN is not a ZDN is distribution. Theta dn it is ZDN. Okay, you can say probability of ZDN given theta d. I agree. Not really. Why should we multiply them? I don't get this part. And then WDN, it makes sense. This part makes sense. The first part, inference objective. Alright, let me fix this part. We want to compute this posterior, but this is interior to compute it. Theta and z. Allocation of topics and what are betas we have omega. The words we got approximation q of theta dz d given lambda gamma d and phi d. Q of theta d given gamma d z dn given phi dn. What does this stand for? Phi theta dn. each document we have a mixture, right? I agree. Okay. It's not 1 to K, it is 1 to D for topics. Exactly. Okay, makes sense. Okay, makes sense. Okay, think that we want to be alright, not 1 to K. Theta K is not, it's not theta K, theta 1. It's for document 1 to document D. They have their own mixture. Alright, makes sense. Gamma phi theta z. K was topic. K word psi of gamma k alpha k. Okay, gamma is similar to alpha. Word sum of the phi of the word, where psi is the digamma function. Repeat until convergence. Well, motherfucker, what are the intuition for gamma and phi? Sorry. Gamma phi. represent theta. Okay, well, I can compute 2 plus here, so we are working with a simpler compute theta z parameter. That's good to know. Gamma, how we represent theta. Topic mixture for a document. Gamma. What is gamma? How we represent theta. Topic mixture for a document. Okay. Okay, it is, it stands instead of theta. Alright. Phi instead of beta, how we represent each word's topic assignments at the end. So instead of z, we are zdn, we are using phi, and psi, the gamma function, it pops up in the expectation of the distribution. Now understand them. For VDN, how likely is the word WDN to come from each topic? Okay. Gamma here. Not theta, what is the other one? Best guess. So if we wanna do that, we wanna change not the z phi. Oh, it uses phi. We wanna change betas. Okay. Go. Guys, I have to stop. a simpler tractable distribution and optimal. This is textbook. Alright, this was established before. Scalable and showing the inference can be done. So for that that's the famous formula, we can get deep in it, not now. Oh, Dirichlet and multinomial are conjugate, expectations are tractable. So EM. Okay, guys, I'm gonna stop. Maybe one round of counter. One round.
Let's roll.
Who's shooting? This motherfucker kills me every time. Hmm.